Deploying modern large language models requires massive server racks, extreme memory bandwidth, and constant cooling. To run these on consumer hardware, we have to aggressively compress them down. The deployment gold standard right now is joint W4, A4, KV4 quantization. This process squashes the model's weights, its activations, and its key value cache down to just 4 bits of memory each. This diagram illustrates the baseline math of asymmetric quantization. We take a high-precision FP16 tensor and map its values onto a fixed 4-bit integer grid, ranging from -8 to +7. This mapping works efficiently until the system encounters a massive 6 sigma activation outlier. To contain this magnitude, the scale factor S expands. When boundaries stretch to include the outlier, normal data points instantly collapse into a single 0-point bin. The extreme magnitudes in specific activation channels destroy the resolution of the low-bit quantization grids. The network can no longer distinguish between subtle values, introducing quantization errors that lead to a failure in model logic. To mitigate this, the prevailing industry strategy is to apply a rotation matrix, transforming the activation distribution before quantization occurs. By multiplying the tensor by a Hadamard matrix, the mathematical properties of computational invariance are leveraged to smear the outlier's extreme magnitude evenly across all dimensions. The technique has evolved. Early implementations like Quarot used randomized Hadamard matrices. Current methods like SpinQuant actively learn the rotation matrix through gradient descent to optimize the distribution. This graph plots calibration sample size against output variance, highlighting the engineering cost of the SpinQuant method. Optimizing the rotation matrix is notoriously data-hungry. If you reduce the massive calibration datasets, the variance spikes significantly. Standard engineering practice assumes that outliers are strictly destructive artifacts. The prevailing logic states they must be carefully clipped or smoothed out of the training data. Attempting to strictly sanitize activation data during rotation training paradoxically yields a fragile rotation matrix. The resulting system is data-hungry and highly susceptible to variance. The spin-out method relies on an entirely different thesis. We solve the outlier problem by intentionally injecting synthetic outliers directly into the transformer's activation layers. Transformer layers do not react to outliers equally. Applying a blanket injection of extreme values across the entire network would cause immediate computational instability. This equation calculates the layer sensitivity score. It acts as a targeting system to isolate the layers requiring intervention. The formula combines baseline kurtosis, measuring heavy tails, with downstream performance degradation, delta E, flagging the most vulnerable layers. A greedy search algorithm evaluates these scores, iteratively testing combinations to build the optimal targeted subset. This scoring mechanism allows us to identify the targeted layers where artificial outlier injection yields the most significant increase in global stability. Once the target layers are isolated, the search phase ends and the active training phase begins. This equation illustrates the creation of the synthetic outlier batch. The delta variable generates an array of exactly 30 distinct synthetic values. These 30 values are scaled to the maximum absolute value of that layer's activation input. The protocol then inserts these values into random positions within the activation vector. The immediate isolated statistical impact is a significant spike in the long tail of the data distribution. Injecting precisely 30 values is mathematically deliberate. It stretches the tail while preventing the core statistical measures, like the mean and variance, from completely collapsing. By controlling the injection size, we successfully engineer an artificial heavy-tailed distribution without destroying the layer's baseline mathematical integrity. This chart tracks internal statistical changes. Synthetic outlier injection increases kurtosis, while mean and variance remain flat. The second graph connects this inflated kurtosis to an exponential increase in the gradient norm. The spin-out gradient tracks strictly above the baseline. The specific optimization algorithm tasked with processing this gradient and updating the rotation matrix is called Cayley-SGD. Cayley-SGD operates under a strict geometric constraint. It must optimize strictly on the Stiefel manifold to maintain perfect matrix orthogonality. This equation is the exact Cayley-SGD update rule, displaying the internal mechanics of the optimization step. Notice the skew-symmetric matrix Y. This single variable controls the magnitude of the update. Embedded inside the Y matrix is the G variable, the gradient. The artificially large gradient norm caused by the synthetic outliers forces a significant scaling of the Y matrix. This enlarged Y matrix then forces Cayley SGD to make larger, more aggressive iterative updates to the rotation matrix R. The synthetic noise acts as a regularizer. It propels the optimizer out of weak local minima, forcing it to construct a matrix neutralizing extreme values. Transitioning to the post-training inference phase, we evaluate the hardened rotation matrix against real data. This split-screen chart proves the squashing effect. The original distorted distribution on the left transforms into a perfectly uniform distribution on the right after spin-out rotation. Because values are evenly distributed, kurtosis across zero-shot tasks collapses to a near-zero baseline. The accelerated gradient signal generated during training also produces major workflow efficiency gains. This table compares the resource requirements. Calibration data drops from 800 samples down to 200, and performance variance drops from 0.3 to 0.23. Faster optimization and lower variance directly yield state-of-the-art W4A4 KV4 perplexity, locking in at a score of 5.81 on the Llama 2 model. The initial professional instinct was that activation data had to be perfectly sanitized and clipped before rotation training. Attempting to protect the optimization algorithm from outliers creates a brittle matrix that leaves the final deployed model defenseless against real-world anomalies. Algorithmically leaning into the distortion, deliberately poisoning the data, provides the exact mathematical leverage required to survive deep 4-bit compression. When operating on the Stiefel manifold, the most robust defense against extreme data anomalies is mathematically engineered, calculated exposure to them.